Have you ever been playing a game and just, I don't know, almost subconsciously noticed how right everything feels? Like a boulder rolling down a hill and it just has that believable
Oh,
weight.
you
And
know, or like a bouncy ball hitting a wall and
yeah,
it ricochets perfectly.
exactly. Games can really capture your imagination when they get that realistic movement and interaction down. But it makes you wonder, doesn't it? How do developers pull that off? Getting that natural motion, the collisions, gravity, all without having to build a physics engine from the ground up every single time.
Right? It's a huge task if you had to do it all manually.
Okay, so let's unpack this a bit. Today, we're diving into exactly that, the heart of realistic game movement, which is the physics behavior in Construct 3.
Mhm.
Imagine being able to make things bounce, roll, collide, just like they would in the real world, and crucially, without needing a PhD in physics. It's this incredibly powerful toolkit for bringing game worlds to life.
And what's really fascinating, I think, is how Construct 3 makes this accessible. It empowers creators, even folks without deep coding skills or a math background, to simulate these really complex physical things.
Yeah, it really opens the door.
It does. It sort of democratizes that aspect of game dev. So our mission for this deep dive is basically to pull out the core ideas from the Construct 3 documentation about this physics behavior. We want to help you understand not just what it does, but maybe more importantly, why these specific tools and settings are so crucial for making compelling dynamic games.
And the great thing is our source is straight from the horse's mouth, so to speak. It's directly from the Construct 3 documentation itself.
Yeah, no secondhand interpretations here.
Exactly. We're getting a direct look at how this engine handles physics. It's like getting the official manual, but, hopefully a bit more engaging and discussed.
The context, yeah.
So let's start right at the beginning. The absolute foundation. What is the physics behavior in Construct 3? Well, at its core, it's essentially a pre-built tool, right? Designed to simulate realistic object physics. Think about gravity pulling stuff down, things bumping into each other, having weight, momentum, maybe even air resistance.
All those interactions that make a world feel, well, real.
Right. The physics behavior bundles all that up for you.
And here's a really key piece of info, especially if you've messed around with game dev before. This isn't just some simple thing they built from scratch. It's powered by Box2D.
Ah, okay. Box 2D.
Yeah, Box2D. It's a really well-known, robust, open source 2D physics engine. It's been used in tons of games, mobile hits, indie games. It's everywhere.
So you're getting something industry standard, basically.
Exactly. You're not getting a rough approximation. You're getting a tried and tested engine.
Right.
Which is great news because it means you can expect pretty consistent, reliable, optimized physics.
That makes sense. It gives it credibility.
It does. And it means if you look up general 2D physics stuff online, or maybe you've used Box2D elsewhere, a lot of the concepts will feel familiar. It lets your objects interact with forces, collisions, gravity, all that, in a way that just feels natural.
Okay, but it's not simple, right? The documentation itself admits it's relatively complex.
Yeah, they don't sugarcoat it. It's powerful,
Yeah.
but there's a learning curve if you want to really master it, especially for complex interactions.
So because of that, the docs recommend some starting points, and we should probably echo that advice. They strongly suggest checking out their tutorials. Physics in Construct, the basics, and physics in Construct, forces, impulses, torque, and joints.
Definitely. Those aren't just like optional reading.
No, they frame them as pretty critical foundational knowledge, stuff that'll save you a lot of headaches later.
Absolutely. And connecting this back to game design,
Mm-hmm.
understanding those underlying physics principles makes you a way more effective designer, even if the engine does the math. Well, those tutorials, they go beyond just showing you buttons in Construct. They explain how physics engines generally work, they talk about different joint types, and crucially, they explain the difference between forces and impulses, something that trips up a lot of people.
Okay. Yeah, I can see that being important.
Right. If you grasp those concepts, you can actually figure out why your object isn't behaving right, instead of just randomly changing numbers. You can optimize things better. It's like
Mhm.
knowing how to drive versus understanding how the car's engine works. One lets you get around, the other lets you tune it and fix it.
That's a good analogy. Okay, so that leads us to something really crucial the documentation points out. A potential pitfall, maybe. The difference between the physics simulation and the construct layout.
Ah, yes, the synchronization challenge.
Explain that.
So the physics behavior runs its simulation kind of separately from where Construct draws your sprites on the screen, the layout. They're linked, obviously, but they're distinct processes.
Then why is that a challenge?
Well, The documentation warns about unpredictability.
Hmm.
Let's say you have a ball rolling, handled by physics. If you try to use a standard construct action, like set position or set angle, to move that ball,
Things go weird.
things can go very weird. What happens is, construct basically tells the physics simulation, hey, this object is now here. It teleports it instantly.
Without considering the physics.
Exactly. It
Yeah.
doesn't simulate the movement to get there. It doesn't check for collisions along the way. So you might suddenly have objects stuck inside walls or overlapping weirdly or just behaving erratically because the physics engine's internal state just got completely messed up. It loses consistency.
Okay, so that sounds like something you really want to avoid.
Definitely. Which leads to what you called the golden rule earlier.
Right. The documentation is pretty clear here. It's highly recommended, like really strongly advised, that you control physics objects only using the physics behavior's own actions.
Mm-hmm. Apply forces, apply impulses, set physics velocity, use torques. Stick within that system.
Don't try to use the standard set position or set angle actions on physics objects.
Generally, no. Stick to the physics actions. That keeps the simulation stable, predictable, reliable. It's fundamental.
Okay, got it. And speaking of avoiding confusion, the docs also clear something else up about behaviors like solid or jump through.
Ah, yeah, the redundant ones. It says they're totally redundant and have no effect if an object already has the physics behavior.
So why are they even there then? That seems confusing.
Well, they're for non-physics objects. If you just need simple basic collision without a full physics simulation, maybe for UI elements, or very simple static obstacles in a non-physics game, that's when you'd use solid or jump through.
Okay, so for physics objects, if you want something to be like a solid wall or the ground,
You don't use the solid behavior. You use the immovable property within the physics behavior settings for that object.
so there's physics equivalent.
Exactly. It achieves the same goal, making it unmoving, but it does it within the physics simulation, so it interacts correctly and stably with everything else that's using physics. It's a subtle difference, but really important for setting things up cleanly.
Right, that makes sense. Okay, so we've got the basics down. Let's dig into actually sculpting the world. Let's talk about the properties you can set on these physics objects. These are the things that define how an object is physically, right?
Exactly. Their inherent characteristics.
First one, immovable. We just mentioned it. If you check this box.
It basically gives the object infinite mass in the simulation. Its density gets ignored and it just doesn't move. No matter what hits it, no matter what forces you apply, it's fixed.
So perfect for things like the ground, level boundaries, static platforms.
Absolutely. The unyielding parts of your world, the anchors. You need those stable elements for everything else to interact with. Trying to push an immovable object won't do anything. It stays put.
Okay, next property, collision mask. This sounds important. It's how the object physically interacts, shape-wise.
Precisely. It defines the physical shape used in the simulation, which might differ from how it looks visually. You got three main options.
What are they?
First is use collision polygon. This tells Construct to use the custom collision shape you can draw in the animation editor. If you haven't drawn one, it just defaults to the object's simple rectangular bounding box.
Good for complex shapes, then.
Yeah, for matching the physics shape closely to the visuals. Second option is just bounding box. This forces it to always use the simple rectangle around the sprite, ignoring any fancy custom polygon you might have drawn.
Simpler, maybe faster.
Generally, yeah. Less complex calculations than a detailed polygon, but less accurate for non-rectangular sprites.
And the third one, circle. This one seems interesting.
Ah, yes. The circle option. This was a bit of an aha moment for me, too, when I first really got it. It completely ignores any collision polygon or bounding box. It just treats the object as a mathematically perfect circle for all physics calculations.
And why is that so useful?
Because, as the docs point out, it allows objects to roll smoothly. Think about it. A polygon, even one with tons of sides that looks like a circle, is still made of tiny straight lines. It can't roll perfectly smoothly. It'll have microjolts.
Ah, right, like trying to roll a stop sign?
Kind of. But a perfect circle collision mask that lets things like barrels, balls, wheels roll without any hitches. It's crucial for that kind of motion.
So the choice of collision mask massively impacts how an object feels and behaves, even if the sprite looks the same.
Absolutely. You can have a sprite that looks like a square, but give it a circle collision mask, and it'll roll like a ball. which could be weird or maybe exactly the effect you want.
Yeah.
But if you want realism, you generally want your collision mass to reasonably match the visual shape and function. A visual circle with a bounding box mask will feel awkward when it tries to roll.
Okay, good tip. What about prevent rotation?
Pretty much what it says. It stops the object from rotating, but only rotation caused by physics collisions.
Only from collisions, so other things could still rotate it.
Exactly. If you apply torque using an action, or set its angular velocity directly, it can still rotate. This property just stops it from tumbling over when something bumps into it.
Useful for characters, maybe, to keep them upright.
Yeah, player characters often use this, or maybe things like crates you don't want easily tipping over. It maintains stability during physical interactions.
Got it. Next, density. This determines mass, somehow.
Yeah, mass in the physics simulation is calculated from density multiplied by the area of the collision mask shape.
Okay.
But here's the key thing the docs highlight. Exact density values used are not important. Only the relative density is significant. There are no specific units like kilograms or anything.
So it's just about comparing objects.
Precisely. An object with density 6 is simply twice as dense and therefore twice as massive as an object with density 3, assuming they have the same collision area. This relative mass affects how much inertia an object has, how hard it is to push, how much it pushes back in collisions. You don't need real-world density values. Just decide. Is this boulder much heavier than this wooden crate? Okay, give the boulder a density of, say, 100 and the crate 10. The ratio is what matters to the simulation.
Makes sense. How about friction? Sounds straightforward.
It is, mostly. It's a value from 0 to 1. 0 means no friction at all, like perfectly smooth ice. 1 means maximum friction, like sandpaper or sticky glue.
And this affects sliding.
Yep, how easily objects slide against each other when they touch. Low friction means things slide easily, keep moving longer. High friction means they slow down quickly, maybe even stick. Essential for different surfaces, ice levels, rough ground. And remember, it applies between moving objects too, not just against static ground. Stacks of crates might slide off each other differently based on friction.
Right, okay, similar range for elasticity.
Yeah.
0 to 1.
Correct. Elasticity is basically bounciness, or restitution is a technical term. 0 means totally inelastic, like dropping a lump of wet clay. It hits, it stops, no bounce.
Splat.
Exactly. 1 means perfectly elastic, like a super bouncy rubber ball that bounces back to its original height, theoretically. Most things are somewhere in between, so you'll use values like 0.5, 0.7 to get a natural feeling bounce.
Pool balls would be high elasticity.
Very high, yeah. Makes them bounce off each other, predictably. You could use a bouncy object as a puzzle mechanic or an inelastic one to block something permanently once it lands. Big impact on feel.
Okay, 2 more properties that sound related. Linear damping and angular damping.
Right. Think of these as drag or resistance. Linear damping affects slowdown for straight line movement. Again, 0 to 1.
0 means?
0 means no slowdown at all. An object moving will just keep moving forever at that speed unless something else hits it, like in a vacuum. 1 means maximum slowdown, it'll lose speed very quickly.
So this simulates air resistance. Or water.
Exactly. Air resistance, water resistance, moving through mud, whatever drag you want in your environment. Low damping for space. High damping for underwater levels where movement feels sluggish. It controls that overall flow.
And angular damping is the same, but for spinning.
Precisely. Same 0 to 1 range. It controls how quickly a spinning object loses its rotational speed. High angular damping makes spins die out quickly. 0 means it spins forever unless stopped by something else. Important for making sure things don't just spin endlessly, which can look weird or even hurt performance.
Okay, what's bullet? Sounds specific.
It is. This is for enhanced collision detection, specifically for really fast-moving objects.
Why would you need that?
Because sometimes objects moving extremely fast can pass through other objects between physics steps. The engine checks position, then checks again a fraction of a second later, and if the fast object was entirely on one side and is now entirely on the other, it might miss the collision completely. It's called tunneling.
Ah, like a bullet phasing through a wall.
Exactly. Enabling the bullet property makes the engine do more rigorous, continuous collision checks for that object.
Right.
But there's a big trade-off. The docs clearly state this can affect performance.
So only use it if you have to.
Yes. Only turn it on if you're actually seeing tunneling issues with specific fast objects, like projectiles. Don't just enable it everywhere thinking it's universally better. It's a fix for a specific problem at a performance cost.
Got it. Last property. Enabled. Simple toggle.
Yep. Just turns the physics simulation on or off for that object. If it's disabled, it's basically invisible to the physics world. Other physics objects will pass right through it like it's empty space.
Useful for picking things up
Yeah.
or temporary effects.
Both. Maybe a player picks up an item, you disable its physics while they carry it. Or maybe a ghost character needs to pass through walls, so you disable its physics, then re-enable it later to make it solid again. It lets you dynamically change how objects interact.
Okay, that covers the what they are. Now, how do we check their state and make them do things?
Conditions and actions, right? Right. Conditions let you ask the physics world about its state, and actions let you tell it what to do.
So what can we check with conditions?
You can compare angular velocity to see how fast something is spinning in degrees per second. Positive is usually clockwise, negative is counterclockwise. Good for checking spinning platforms or fans.
Okay.
You can compare mass, check its calculated mass based on density and area. Maybe apply different logic to heavy versus light objects. You can compare velocity, either the overall speed or speed just on the X or Y axis. Super useful for movement logic. Trigger effects on high-speed impacts. Check if something has stopped moving.
That sounds very handy.
And then there are simple checks like is enabled or is immovable to confirm its current physics state. Oh, and an interesting one is sleeping.
Sleeping, like taking a nap?
Sort of. It's an optimization. Physics engines are smart. If an object comes to a complete rest and isn't interacting with anything, the engine puts it to sleep to save CPU power. It stops processing it constantly.
Okay.
The as sleeping condition tells you if an object is currently in that low power state. Sometimes objects might look stopped but are actually moving infinitesimally, preventing sleep, which could be a tricky performance issue to debug sometimes.
Right. So conditions let us check things. What about making things happen? Actions. You mentioned forces and impulses earlier. That distinction is key.
Absolutely crucial. This is fundamental to making things move realistically. When you use apply force, you can apply it at an angle towards a point or just give X and Y values you're causing acceleration.
Like pushing a box.
Exactly. It's a continuous push. As long as the force is applied, the object speeds up or changes direction gradually.
Okay, and apply impulse.
Impulse is like a sudden hit or kick, a bat hitting a ball, a character jumping. It's an instantaneous change in velocity, a one-time whack.
So jump, impulse, rocket engine force.
Perfect examples. Using force for a jump often leads to that floaty, constantly accelerating upwards motion, which usually isn't what you want. You want that quick burst of upward velocity from an impulse. Understanding the difference is key to getting the feel right.
And when you apply these, there's something about image points.
Right, where on the object you apply the force or impulse matters. If you use image point 0, that typically means the object's calculated center of mass. Applying force there causes no rotation, only linear movement.
Okay.
If you use -1, that usually means the object's origin point, where the XY coordinates are. Applying force there might cause rotation, depending on where the origin is relative to the center of mass.
And any other image point.
Any other numbered image point you've defined on the sprite will almost certainly cause rotation because you're applying the force off-center. It creates torque, a spinning effect. It's a neat way to control both movement and spin with one action.
Clever. Okay, besides forces and impulses, can you just set the speed directly?
Yep, there's set velocity. You just give it the desired speed in pixels per second for X and Y. It's very direct, kind of overrides the physics simulation's momentum calculations for a moment.
And that relates to teleport. You mentioned that versus the normal set position.
Ah, yes. It's a common question. Why use the physics teleport action instead of the layout set position action if you need to instantly move a physics object?
Yeah, what's the difference?
The crucial difference is that teleport moves the object's position without changing its current physics velocity. Set position might interfere with velocity or cause instability.
So like for a portal.
Exactly, the perfect use case. A physics object flies into a portal, you use teleport to instantly move it to the exit portal's location. Because teleport preserves the velocity, it comes out the other side still moving at the same speed and direction it went in. Seamless.
Yeah.
If you used set position, its momentum might get reset or become unpredictable.
Okay, that's a really important distinction. Now, what about settings that affect everything? Global physics settings.
Right, these actions change the rules for the entire physics world, not just one object.
Like collisions?
Yeah, enable-disable collisions. By default, all physics objects collide with all others. This action lets you say, for example, player objects should no longer collide with enemy objects. It affects all players and all enemies.
Useful for power-ups or specific interactions.
Definitely. But there's a big warning. If you re-enable collisions between object types, while some instances are already overlapping, the physics engine will try to violently push them apart to resolve the overlap.
The explosion effect again.
Exactly. It can look really bad, cause instability. So if you're turning collisions back on, you might need to manually check for overlaps and maybe teleport objects apart first. Use with caution.
Okay, what about set stepping iteration? Sounds technical.
It is a bit. It controls the number of velocity iterations, default 8, and position iterations, default 3. The Box 2D engine performs each physics step.
And what do those iterations do?
They basically determine the accuracy versus performance trade-off for the whole simulation. More iterations mean higher accuracy, better handling of complex collisions, less chance of objects sinking into each other or tunneling, but it costs more CPU power.
Fewer iterations means faster performance, but less accuracy.
Right. You might see more visual glitches or instability with fewer iterations, especially with fast objects or complex stacks. For simple games, the defaults are often fine. For something with really intricate physics, you might need to increase them, but watch your performance. It's a balancing act.
Okay. And set stepping mode. That affects time.
Yeah, how the physics simulation advances time. The default is framer independent. It uses DT delta time, the time since the last frame, to try and keep the physics speed consistent regardless of the player's screen refresh rate.
So a ball falls at the same real-world speed on a 60 hertz or 144 hertz monitor.
That's the goal. But the docs mention a downside. It can produce non-deterministic results. Tiny floating point math differences mean the exact same inputs might not always produce the exact same outcome.
Ah, tricky for multiplayer.
Potentially, yeah. Also, to prevent chaos, if the frame rate drops massively, it clamps the maximum time step to about 130th of a second. Stops physics explosions during big lag spikes.
What's the alternative mode?
Fixed. This mode always uses a fixed time step, specifically 160th of a second, no matter the frame rate. This makes the simulation fully deterministic. Same inputs always give the exact same results. Great for netcode synchronization or perfect replays.
But the downside?
The perceived speed will change with frame rate. On a 120 Hz monitor, the physics might seem to run twice as fast as on a 60 Hz monitor because it's stepping forward based on a fixed real-world time interval, not the screen refresh. Big trade-off.
Yeah.
Consistency versus determinism.
Okay, last global one. Set world gravity. Easy enough.
Pretty straightforward.
Yep.
Adjust the overall gravitational pull affecting everything. Default is 10 downwards on the y-axis.
Lower for moon gravity, higher for Jupiter gravity.
Exactly. Or 0 for space. You can even change the direction, make gravity pull sideways or upwards for crazy effects. It instantly changes the feel of movement and jumping for all physics objects. Great for themed levels or dynamic gameplay changes.
Cool. Okay, beyond properties and global settings, there are joints, connecting things together.
Yes, joints are super powerful for creating mechanisms. They link two physics objects.
Like what?
Well, create distance joint fixes two objects a set distance apart, like they're linked to a rigid pole. Think wrecking balls, chains. You specify the points on each object to connect. Remember, image point 0 is center of mass. Model 1 is origin effects rotation.
Okay, what else?
Create revolute joint. That's like a hinge. It pins two objects together at a point, letting them rotate freely around it, like a door or a pendulum.
And limited revolute joint.
Same hinge idea, but you set angle limits. It can only rotate within a specific arc, like a bell clapper that only swings so far, or a drawbridge. Essential for controlled rotation in mechanisms.
Makes sense. Any others?
Create prismatic joint. This is a sliding joint.
Yeah.
It restricts movement between two objects to a specific axis, like they're on a rail.
Like an elevator.
Exactly. You can set limits so it only slides so far. And you can even enable a motor on the joint to apply a constant force along that axis, making pistons, sliding platforms, that kind of thing. Very versatile.
How do you get rid of joints?
Remove all joints. Action does the trick for a specific object. But remember that warning.
The overlap issue again?
Yeah. Joints often automatically disable collisions between the connected parts. If you remove the joint, those parts might now be overlapping. If collisions are still enabled or get re-enabled, they'll suddenly push apart violently.
So disable collisions manually after removing the joint if you anticipate overlap.
Or teleport one object slightly away before re-enabling collisions. Just something to be very aware of to avoid that jarring effect.
Good point. Okay, under object settings, there's set awake. That relates to the sleeping thing.
Exactly. We mentioned objects go to sleep to save CPU when they stop moving. But sometimes, something external might happen near a sleeping object, and it should react, but it's still asleep.
So set awake wakes it up.
Yep. It forces a sleeping object back into active simulation so it becomes responsive again immediately. You usually don't need to mess with this much as the engine handles waking things on collision, but it's there if you need to force responsiveness after, say, a non-physics change nearby.
Got it. And finally, actions for rotation. Torque.
Right. Torque is rotational force. Apply torque causes rotational acceleration, makes things spin faster or slower. It's the spinning equivalent of apply force.
And you can set rotation speed directly too.
Yep, set angular velocity. Just like set velocity for linear motion, this instantly sets the spin rate in degrees per second, bypassing acceleration. Your main tools for making things spin dynamically: fans, platforms, character attacks.
Phew. Okay, that's a lot of ways to control things. But
Okay.
how do we get information back out? Expressions.
Expressions are your sensors into the physics world. They let you read real-time data.
Like what?
Angular velocity gives you the current spin speed. Center of mass x and center of mass e give you the calculated center point, which, remember, depends on the collision mask, not always the visual center.
Okay.
Contact count tells you how many points the object is currently touching other physics objects. Is the character on the ground? Count 0 probably means yes.
Can you find where it's touching?
Yes. Contact XA index and contact Y index give you the exact layout coordinates of a specific contact point, useful for precise hit detection. You can also get mass, the calculated mass, and velocity x, velocity y for current speed on each axis.
So you could calculate impact force from mass and velocity.
Absolutely, and you can also read the current values of properties like angular damping, density, elasticity, friction, linear damping, useful for debugging or maybe basing logic on current object state.
So connecting it all together, these expressions are how your game knows what's happening in the physics simulation.
Exactly. They're the feedback loop. They let your events and logic react dynamically. Is the player standing still? Check velocity x, y. Did the bullet hit hard enough? Check velocity at impact. Are all wheels touching the ground? Check contact count for each wheel. They turn the physics simulation from just a visual effect into something your game can actively respond to and build logic around.
Wow. Okay, we've really covered a lot there. Taking this deep dive into the physics behavior in Construct 3, it's clear it's an incredibly powerful system, isn't it?
It really is an amazing toolkit for dynamic motion.
From setting up those basic properties, density, friction, bounce that define how things just are, to applying forces, impulses, connecting things with complex joints, Construct 3 gives you so much control.
And I think the core insight, the really valuable thing, is that balance it strikes. You've got the power-of-the-box 2D engine doing the heavy lifting, handling the complex math. But your understanding of the concepts, forces versus impulses, why collision masks matter so much, especially that circle option for rolling, the nuances of global settings like stepping modes. That knowledge is what lets you use the tools effectively.
It translates directly into better game mechanics.
Totally. More robust, more believable, more fun. It's about using the tools intelligently, knowing the why behind the settings, not just tweaking randomly. That's what lets you make things move intentionally and make them feel right.
So as people listening start thinking about using this in their own games, platformers, puzzles, whatever, here's a thought to leave you with.
Okay.
How could you use dynamic changes to the world's physics? Like, what if you manipulated world gravity during gameplay? Or changed friction dynamically? Could you turn a simple platformer into something completely unpredictable? Maybe create puzzles that rely purely on adapting to sudden shifts in environmental physics?
Oh, that's interesting. Like gravity shifting sideways or suddenly becoming super bouncy.
Exactly. Once you really grasp these tools, the potential for unique gameplay based on physics itself, it seems pretty vast.